As discussed in the very first video in this series, talking about the definition of differential equation, we can actually classify differential equations according to type, order, linearity, and so on and so forth. This video will talk about the types of differential equation or the classification by type. And this is also connected to the previous video talking about the difference between ordinary derivative and partial derivative, because there are two types of differential equations. The first one is an ordinary differential equation, and the second one is partial differential equation. So let's talk about the first one, ordinary differential equation. Its definition could actually talk about a certain equations, differential equation that contain only ordinary derivatives of one or more unknown functions with respect to one single independent variable. Again, in the previous video, we talked about ordinary derivatives. So we will be using that here as well. One example of an ordinary derivative, if we have a certain function that can be expressed in a term of a x, okay? So it's a function of y in terms of x. The first form or the first sample of what do you call this one, ordinary derivative, is discussed as this one, the first order derivative of y with respect to x. We know that again, this is actually our independent variable and this is our dependent variable. So we only have one independent variable, and if this is actually on this a certain differential equation, only this form or even its higher orders, then we can call it an ordinary differential equation. One example I'm going to provide here is, say for example, the first order derivative of y with respect to x is equal to 3y. This is an example of an ordinary differential equation because it contains a ordinary derivative, and with respect to one variable x, very clear, we only have one or single independent variable there, and y is actually our unknown function. Similarly, if you're going to have a second order, let's say the second order derivative of y with respect to x, let's say plus the first order derivative of y with respect to x, and let's say minus 6y is equal to 0. This is still an example of an ordinary differential equation because we have here ordinary derivatives. This is the ordinary second order derivative. This is an ordinary first order derivative. And if you can see, we still have the same independent variable, which is x. We have only one singular independent variable. Now, what if I have this example? Okay, we have here the first order derivative of x with respect to t plus the first order derivative of y with respect to t is equal to 2x plus y. This time, we have two unknown functions, or specifically two dependent variables. This is still okay because we have here ordinary derivatives of one or more unknown functions. So this is an ordinary derivative. This is ordinary derivative. For the first one, this is actually the ordinary derivative of x function or function of x with respect to t, and this is also an ordinary ordinary derivative of function y with respect to t. Even if we have two functions now, we can still see here that our independent variable t is still the same. We have a singular independent variable. So this is still an example of an ordinary differential equation. Okay? Now, to differentiate that to the second form, we call partial differential equation. So basically, this also contains partial derivatives. So we have here an equation, okay, involving partial derivatives. And we have discussed already when can we say that a certain derivative is partial of one or more unknown functions of two or more independent variable. The two things here that you need to consider is the idea of really having partial derivatives, and you have two or more independent variables. Okay, as discussed already, the partial derivatives will come in with this notation. This actually notation using delta. Okay, this is also another way or nicer way to write delta. So say for example, if we have here the partial derivative of f with respect to x, stating that our function f has two variables, let's say x squared y plus 3y. So we can actually come up with a partial derivative of function of f with respect to x, treating y as constant, and another one is the partial derivative of f with respect to y, treating treating x as constant. At this time, we can see that there are two independent variables using the notation for partial derivative. Let us have other a more formal example to this. Say for example, we have this form. Okay, the partial derivative. Let me use another color. The partial derivative of u with respect to x plus the partial derivative of u with respect to y is equal to 0. Obviously, it contains partial derivatives, and at the same time, it also includes different independent variables. So you have here x and y. So it fits two or more independent variables. Okay? So some other examples would look like this. If you have, say for example, the partial order second order derivative of u with respect to, let's say, t is equal to 5t minus the partial order derivative of, let's say, y with respect to x. Here we it's partial second if we're talking about second, so sorry for that. It should be here. Okay, I forgot. So second, both of them are second order and they are both partial derivatives. So we can see here that we have two functions, two dependent variables. We have here, okay, u and y. These are your dependent variables. So this still fits the definition to one or more unknown functions. And clearly, we also have two independent variables t and x, and they are actually under the same equation, considering that they are talking about partial derivatives. So this is an example of a partial differential equation. This is how we differentiate both of them. We'll have an example or another video talking about the difference or identification whether a certain differential equation is a partial differential equation or an ordinary differential equation. So please stay tuned with that. Thank you very much for watching.